this session, we're going to talk about SN1 substitution, nucleophilic can be neutral or minus, unimolecular, and also we're going to talk about the SN2, or substitution, nucleophilic, bimolecular. These are two substitution reactions that are different ends of the spectrum. Now, I want to review here. We have some models that we're going to show in just a little bit. But the substitution, we're talking about, say, in the case of SN1, you're probably going to have 2 or 3 alkyl groups on the carbon with a good leaving group. Now, one example would be of this. This is an ionization process. It's a 2-step process, but it's unimolecular. So we need to talk about what we mean by unimolecular. But let's take something like hydrogen chloride. You put it in water. The water splits the species apart. You get X minus solvated, and you get H3O plus solvated. So this would be an ionization. This process is an ionization also. And what happens here is if you have appropriate solvent and a good leaving group, what we call a leaving group here, 2 or 3 R groups on it in a polar solvent. Now, it cannot be water most of the times because the organic compounds have to be soluble. There has to be some alcohol or something like that in there. But this group here, this molecule here, can take and ionize, and you get the intermediate carbocation, and you get the X minus. Now this X minus becomes a nucleophile, and in this case, this is a transition state. So there's only one species involved in the rate determinant step. Now, another nucleophile, or the one at left, can come back in, and now you can go on a very fast reaction, and this is going to produce the product, and it can come in from either direction, which we'll see. So that's the SN1, and let's take and look at that in just a second, but let's take a look now at the SN2, and in this case, SN2 means bimolecular, and this is a displacement reaction. A displacement. It's a much more difficult reaction than the other one, or much slower, depending on the system. Now, in this case, you don't want 2 or 3 R groups. You're probably going to have only 1 R group, and you might have a hydrogen, and you even could have a deuterium would be the extreme. In this case, the solvent cannot cause this leaving group to leave. It cannot ionize on its own, and it has to have assistance. And this nucleophile, which usually is negative, not always, it can be neutral, it does have to have a pair of electrons. It has to have an attraction for that nuclear core of the carbon, which has the positive character due to the electronegativity of the X. So this is going to come in from the backside and going to kick this group out. And this is the transition state, and this is the curve. We'll look at the kinetics and so forth in a little bit. But let's take now and look at the model that we have. Here I'm showing, you have to imagine that there's a carbon core, the nuclear core. Now these are the valence electrons bonding the groups on. I have these different colors. I also have them numbered, and I'm showing here 4 different groups. Now, when you have 4 different groups around the carbon, you have something called a chiral or hand-like molecule. What do I mean by that? If I take my left hand and hold it up to the mirror, the image I see would be apparently of my right hand. It's the image of my left hand, but if I took and constructed what I saw in the mirror, I would make my right hand. And this is what we call chiral molecules, and anytime you have 4 groups. Another thing is that we can designate these by 1, 2, 3, 4, and that can be all inclusive. You can have an infinite number of groups. 4 can be anything, but then we talk about priorities. So what I'm showing here is that I've got, this is labeled 1, this would be probably the higher atomic number, 2, 3, and looking through the 4 stuff. If we look through here, we got 1, 2, 3 clockwise, and that's what we call an R structure. You may be familiar with the D and L form, which is used for carbohydrates and amino acids, but this is all inclusive. An infinite number of molecules can have these 4 groups. So you've got 1, 2, 3, 4, that'd be R. Now what can happen is, in the SN1 reaction, the solvent can actually take and pull this group away. So what's going to happen is the solvent is sufficient, and this molecule is such that you've got a good leaving group, and you can have the positive charge, which is left on the carbon fragment, delocalized and spread out. So this can come out and be taken away. This is taken away by the solvent. This is taken away by the solvent. Now I want to go back over this just a couple of minutes time here. What can happen is, if in this case we have the C plus, and there's a carbon in here, and you got 3 different groups on it. And what can happen is this group can, now the nucleophile can come in from the right, and you can get the, I said 1, 2, 3 R, or it can ionize again, and this one can come in from the left. Now if I take and look here, I've got 1, 2, 3, and that's counterclockwise, and this would be what we call the S configuration, and these have opposite configurations. And what would happen here is that you're going to have equal number of the S form and equal number of the R form. But the point is that it is ionizing. It is ionizing, and again, I want to show hybridization here. This is what we call an sp3. There's no p orbitals left, and there's 4 sp3 orbitals. And if they're the same, if these groups are the same, it's going to be perfectly symmetrical, and the bond angles would be 109 degrees in 5 minutes if you took and put the axis through here, 109.5. Now, if I take and let this ionize, what we have now is a trigonal configuration, and you can have a p orbital. A p orbital could be through here. In this case, it's positive, so p orbital be vacant. Okay, so that's what's going to happen. And here, the bond angle would be 120 degrees between any 2 of those groups, talking about axis. So again, the SN1 would be where you have a 4 group system, and it can ionize, and you have the distinct intermediate. So what happens is, as far as the kinetics, and we're going to look at it in a little bit, we're going to look at the kinetics, but what happens is that this is the only group, the only species that's important in the rate determining state. This group does not come in. The solvent can take away and separate these groups, and you get the distinct intermediate. Now a nucleophile can come in, and the same nucleophile, same concentration, it could come in equally from either side, and we get something called, in chemistry we call it racemalization. It would have a 0 optical activity. Now let me talk about what we mean by optical activity. If I take here, I have polarizers here, and I take and have marks on them, so that would be the 0 points. You're getting quite a bit of light pass through there. But if I take this one on the back and rotate it, say about to there, you can see there's not as much light passing through. Now, if I have a solution, and a common one would be sucrose, table sugar, if I have a solution a table sugar, 100 grams to 100 milliliters of solution, and I have a 10 centimeter to 1 decimeter cube, I take and put it in there, and what would happen would be that now the sugar solution would cause the light to rotate to the right, and in this point you would now have the maximum light passing through. So we say it's rotated to the right. But go back to here, in this case, I take and here I have maximum number, I rotate it say 65, 67 degrees, and not as much light going to pass through. If we put a compound that rotates plain polarized light to the right, like sucrose, then you could have maximum light passing through. One system that rotates light to the left would be fructose, which is fruit sugar. Okay, so this is what we have. Now let's look at the other extreme. The other extreme of the systems, and this would be like I say, one where it cannot ionize, and the groups, you've got to have a good leaving group. You've got to have a good leaving group. You've got to have a good nucleophile. Now these groups can be the same. Here it's a nucleophile, here it's a leaving group. And what can happen is that if you don't have enough of alkyl groups to spread the positive charge, this cannot ionize. So we might usually have a hydrogen and it's chiral like this. You could have a deuterium, you could have a methyl group, something like that. That cannot ionize under normal conditions. So what can happen is this group can come in, and it can take and hit, and it can take and drive. It can drive that leaving group out, and there's never a distinct intermediate like we saw in the SN1. So this is called an inversion of configuration. And now I'm showing 1, 2, 3 to the left. That would be S. What I had before is R. So it is totally opposite. Now let me say this about the configuration versus optical activity. This would be the S form. That doesn't mean it rotates light to the left. We don't know which way until you do the experiment or how the light's going to be rotated. But this would be the S form. This would be the S form, 1, 2, 3. This can come in again and knock that group out. Now what I want you to see is, if you notice this is tetrahedral, and at the transition state, the highest energy state along this path, watch the models there and these Easter eggs I have, and watch what happens. If this one comes in, you can see the orange and red pushing to the center and pushing down, and these come through. And at that point you have a trigonal bipyramidal. And this would be the highest point along the way of the transition state. So this is what we mean by 2, SN2. You've got this one in the transition state, the rate determining step. You have 2 groups at the highest point along the way. So again, the SN2 reaction's got to be displaced. If you take and look at the SN1, it's going to ionize. A distinct ionization is going to occur, and now the groups, and these can exist in the solution, and but sooner or later, if you have enough of these, and say if you boil the solvent off or whatever, they're going to come together. But you're going to get a 50-50 distribution, whereas in the SN2 reaction is bimolecular. You're going to get the inversion configuration. So let's take and look at the SN1 again with this in mind here. It's unimolecular. What do we mean by that? It's R3CX takes and the solvent removes the leaving group, removes this group, stabilize it, and you get a distinct intermediate. But this is the rate determinant step. So if we take and look at what that means as far as the kinetics, come over here, I've got the nucleophile. The nucleophile, the group that comes in, is over here. And it does it no matter You got to have enough in there for the reaction to occur. But beyond that, the reaction is so fast that you can double the concentration, triple the concentration, whatever, and the rate stays the same. So that's what we call zero order, zero contribution. Now, what happens is the R3CX is going to be linear. It's going to be first order in the concentration, so you get a curve like this. So if we look at the kinetics here, you got R is equal to, say, a rate constant. This would be the R3CX concentration to a power of 1, means it's first order. The nucleophile is the concentration, whatever it is, but it's to a zero order, so you get 1. So no matter what happens here with this, beyond a certain level, it's not going to affect the rate because it's after the transition state. So if I put 1, whatever the concentration wants to be, we'll make it 1. We'll make this one 1. We get the rate is going to be 1 times the rate constant, 1K. Let's double this. Let's double this one. You got here 2, twice the concentration of power 1, first order. So if you were here, now you're up here. So the rate is first order. But with the nucleophile, it doesn't matter because it's going to be 1, and overall the rate is only doubled. It's 2K. 2K. Now, again, what do we mean by chirality? Chirality is where you have 4 different groups around the carbon. I'm showing some down here. Say this is a methyl group. This would be an ethyl group. This is an isopropyl group in chlorine. So how do we convert these to 1, 2, 3, 4, making it as simple as we possibly can? Well, number one, we look at the atomic number, and it can go on sort of forever because about an infinite number of combinations you can have for organic compounds saturated. But here, the chlorine has atomic number 9, so we're going to give it a higher priority of anything lower, and we're going to look at the ones attached now, the carbon, 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 and there's 6. So I can make this a 1. That's the highest priority. Then I can take and look, when I come here, the C has 3 hydrogens on it. Hydrogen is atomic number 1, low priority. Here I have a C with 2 hydrogen, 1 carbon. It's higher priority than this one. But over here I've got a C with 1 H and 2 carbons attached to this carbon. So we're going to make this the higher priority. And so in this case I'm going to make this into a 2 and it becomes 1. So now what we can do is we can take and use these, and you can learn how to do this. And the thing about it is I have it locked in place here, but no matter what the orientation is, if you visualize through the carbon, through group 4, this is 1, 2, 3 counterclockwise and S, and like I say, those 4 groups could be in the infinite number. So that's what is happening with the SN1. Now let's take and look at the SN2. Again, we're going to look at SN2, and this means bimolecular, substitution nucleophilic bimolecular. And in this case, this group does not have enough of R groups or other groups that can cause a delocalization of the positive charge, and the solvent cannot, under normal circumstances, cannot cause this to ionize. So what has to happen is, using an X minus, but you have to have a pair of electrons. It has to be a nucleophile, a nucleus loving. So it's going to come in and attack the carbon and displace this group. So that is a 1 step. But there are 2 species involved in this rate determinant step. This is the rate determinant step, 1 step. So what do we mean by that? Look at the kinetics again. You notice on the SN1 we had a flat line. Now we do not, because it's first order in the R3CX, first order in the nucleophile. So let's look at the rate, because this is how we can tell in the lab what the reaction is. Now these are the extremes. It could you got it in for a number of positions in between as you switch to groups. Not what we're looking at this. So if we got 1 in here for this concentration, 1 here, you got 1K. If we double the concentration here, it's going to be 2. Double concentration here, it's going to be 2. First order, 2 times 2 is 4. So the rate increases four times by doing that, by doubling the concentration. Chirality we've seen before. We look at the distribution of these 4 different groups. Anytime these 4 different groups on carbon, it's going to be tetrahedral, and it's going to be chiral. Now, let's look at some groups. Well, we could, looking at the extreme here, and this can be done, but let's suppose we have a hydrogen, we have a deuterium, we have an ethyl group. So we only have 1 R group. These hydrogens cannot spread out or delocalize the positive charge as much, and so you cannot get ionization. Let's say we have chlorine again, and if it's attached to the carbon, it's a leaving group. If it's coming in, like I minus or Cl minus, what have you, it's called a nucleophile. So again, the chlorine has higher atomic number, so we put a 1 there. Here we have hydrogen. So this carbon here with number 6, so we'll make this one 2. 2. And so what we have here, well, these have the same atomic number, but the deuterium has a neutron, and so we're going to make this 3. And again, the hydrogen, which is often the case, would be priority 4. So again, you can see how we can switch the groups, and simplistically, we can have 4 different groups, 1, 2, 3, 4, and it can be an infinite number. Okay, let's talk about SN2 reactions. Which one of these 2 mechanisms is going to occur in the human body? Well, the human body is very precise, has to be perfect, everything coordinated, and if we had the SN1 reaction, what would happen would be, we would get, like I say, a equal number here as nucleophile came in, and also the reaction occurs so fast that you're going to get half of one form and half the other form. In nature, things is coordinated and reactions are sped up to a sufficient speed by enzymes. And what is an enzyme? The enzyme would be what my system here, I've got strings using it and all. I can pull the strings. An enzyme is going to do that. It can orient this nucleophile coming in, and it can help remove these groups and all. So it speeds up the reaction very, very fast. So this is the reaction that occurs in the body for the chemistry, because otherwise half of your molecules would be trash.